Okay, well, had a nice long Martin Luther King holiday. Let's hope that was good. And today, since there's no homework due today, I assume there's no questions about the homework due tomorrow. And so we'll just jump right in. Today we are going to learn about trees. Now, I don't know if you guys have done any, probably haven't done any programming with trees yet in your intro class, but you will. And in computer science, a tree is an example of a data structure, and a data structure is a technique or a method or a way to store data. And I don't have time to get into why you would do this and all the different variations of trees, but today what we want to do is take a look at the theory of binary trees. Now binary, what does bi mean? Obviously, it means two. So a binary tree is a tree in which each node in the tree has two children, a left child and a right child. Now here in 12.30 we have the abstract definition of a binary tree, and let's just read that, and then I want to draw some pictures for you. Okay, so first of all, this is an inductive definition. So there is a base case to the definition, and then there is a self-referential part, an inductive part to the definition. Okay, and so let's take a look at the base case. Now, this 0 with a slash through it, that is a binary tree called the empty tree. Have we seen that symbol before? Yeah. So it's the same symbol as the empty set. And so whether that symbol means the empty set or whether it means the empty tree, you just have to tell by the context. Okay, so if you're talking about trees, it's the empty tree. If you're talking about sets, it's the empty set. So unfortunately, the same symbol. So that's the base case, and then the inductive case is parentheses DLR is a binary tree if for all D. Now what does that mean? Colon Z.
Integer.
Integer, right? If for all is a binary tree for D of type integer, and L and R being binary trees. So look, that is basically a non-empty binary tree has three parts to it. It has an integer and a left and a right. L stands for left and R stands for right. Okay? So, and in computer science terminology, that L is called a left child and the R is called a right child, because these trees, when you draw these trees, they look like but they look like genealogy, family trees. You know, your family tree, where you have the parents and each parent has a child. So it's that analogy, a left child, right child. Okay, so what I want to do now is I want to draw four binary trees and show you what they look like visually. Okay, so the first one is going to be, so here these are binary trees, and each tree we'll call T. So the first one is the empty tree. Okay, now to draw the empty tree, I can't draw anything because it's empty. So I mean, it doesn't look like anything. Okay, okay. Here's the empty tree. Here is a we'll just call this tree 1. No, we'll call this, if this is tree, well, this could be tree 0. So here we'll call tree 1 is going to look like this. It's going to have one node in it, and we'll put 5 here like this. All right. So what this represents is the tree DLR, where D it has 5 and L is the left child and there is no left child, and R is the right child and there is no right child. So this is how you would draw it. The way you would write it in this notation would be this. Would be 5 comma empty tree comma empty tree. All right? So this is how you would draw it according to the definition. This is how you would write it according to the definition. This is the way you would draw it on paper. Okay? So here's tree 2. Tree 2 is going to look like this. It's going to have a 5 here, and then this 5 will have a right child, and this right child will be a 3 here. Okay? Now how would you, this is how you would draw it. How would you write it?
5 empty tree 3.
Well, almost, close but no cigar. It would be 5, 5, and then there is no left child, so that is the empty tree. But the right one has to be a what?
Tree.
And our right one has to be a tree. So what is a tree? How do you write down a tree?
3 empty trees.
So it'll be 1, 1.
Well,
Another parenthesis.
yeah, parentheses. It's a tree within a tree.
Okay.
You see what I'm saying? Because it's, here it says DLR. L is a binary tree and R is a binary. But what is a binary tree? It is a parentheses DLR. So we have to have a parentheses DLR here for this tree. But what is this tree?
3 empty set.
Yeah, empty tree. Yeah, so it's 3, empty tree, paren. Now, does everybody see how that works? Okay, and it looks like I'm going to have to use this board here for the next one. So that's tree 2, and here's tree 3. So tree 3 is going to look like this. If we draw this tree, it's going to look like this. 5, 12, 3, 4. Okay? By the way, you know, it's kind of computer scientists, when they draw trees, they draw them upside down. Like, you know, what does a tree look like normally? You have a root, you know, you have the root and the trunk of the tree, and then the branches go up, you know. Well, in computer science, we draw them upside down. The root is at the top, and the branches go down. Okay, but that's just the way they always do it. Okay, but now if this is the way you would draw this tree number 3, if this is the way you would draw, how would you write it?
5, 12.
Huh?
5.
So, okay, parentheses. So this is the top one, right? So this is 5. Now this is the left child.
Paren
So this would be what? Paren,
12 empty set.
empty tree, comma, and then the right one would be this tree. But what is this tree?
3.
It's 3,
Paren
4 empty, empty.
and then yeah, paren, 4, empty,
Paren empty.
close paren.
Don't close it twice.
Oh, don't close it twice. Right. Okay.
Comma empty.
Oh, wait.
Yeah.
Oh, yeah. Comma, empty tree,
Close.
close this paren, and then close this paren. All right. Now, does everybody? So given something written like this, you should be able to draw it, and given you can draw it, you should be able to write it. Does everybody see how that works? Okay. Now, so that's the definition of a binary tree. It's a recursive definition because it's defined in terms of itself. But anytime you have something that's defined in terms of itself, you have to have a base case, and the base case here is the empty tree. Okay. Now we have these definitions. We have definition number: nodes, height, leaf, internal node, and complete. So let's go through each one of these trees and see what each one of these things is. First, 12.31 is the definition of the number of nodes, and that's denoted by the pound, right? And again, it's a recursive definition. What is how many nodes are in the empty tree? What's pound the empty tree? How many nodes are here?
0.
Nothing.
None. There are none. So it's 0. So here let's do, so pound T here equals 0. There are none. Okay? Now, how many nodes are here? Well, according to the definition, okay, is this the empty tree? No. This is not the empty tree, right?
It's 1 node.
Okay, and so what does it say? The number of nodes in this is 1 plus the number of nodes in the left plus the number of nodes in the right.
Which is
Well, so it's 1 plus 0 plus 0. So here, pound T is 1. Are you with? And there's one node. I mean, we draw the nodes with circles visually, all right? And then what's pound t here? What's the number of nodes in this tree? Yeah, there's 2. I mean, obviously there's 1, 2, but I mean, how would you do it? It's by the definition, it's 1 plus 0 plus however many here. But this is 1 plus 0 plus 0. So pound t here is 2. And then over here, number of nodes in this tree is obviously 4. And if you were to do that, recursively, it's 1 plus 0 plus 0 plus 1 plus 1 plus 0 plus 0 plus 0. Yeah, I mean, if you work it all out. But anyway, it's 4. Okay? So that's the definition of the number of nodes. Now, here's a different one, height. Now, when you think of something, if I ask you, how high is this chair? Well, it's like this high, so you're thinking of vertical distance, right? Okay? But the height of it, so what is the height of a tree? Well, the height of this one, so I guess the way we denote height is H-E-I-G-H-T, we spell it out. So here, height of this tree, by definition, what's the height of the empty tree? 0, it's 0. And what's the height of this tree?
1.
Height dot t here is 1. And why is it 1? Because it's, what does this definition say?
It says
It's 1 plus
greater of the 2, what do they call them?
left child and right child. Children, yeah.
The greater
So
of the 2 children, and since they're both 0.
since they're both 0, it's 1 plus 0. Does everybody see that? So it's 1 plus the greater of the height of this and this, so that's 1. And what about the height of this? Now this one's interesting.
2.
This is 4. No, wait, it is 2.
It is 2. Now why is that? It's because it is
The first one plus the greater of 0 or 1.
yeah, it's 1. It is 1 plus the maximum of the height of this and the height of this one and the height of this one. Well, we know that the height of this is 0.
Right.
We know the height of this one is 1, so that one's 2, right? Now, how about this one?
3.
Not 4?
No.
Yeah, you're right. It's 3. And actually, see, the way you can kind of visualize this is like this. It's if you go from here down to here, it's like how many? It's how far down you have to go. 1, 2, 3. See what I mean? That's how you can visualize it. Okay, formally, it's this max. All right. Now, 12.32.1, definition of a leaf. A leaf is a node with no children. That is, it has to have 2 empty subtrees.
Tree 1.
Well, yeah, how many? Yeah, there are no leaves in the empty tree.
Right.
Okay. Is this a leaf?
It is enough.
It is a leaf because it has no children. So this node is a leaf. I don't want to write it down, but anyway, you can see that. Now, is this node a leaf? No. Is this node a leaf? Yes, because it has no children. So this has 1 leaf. This has no leaves. This has 1 leaf. This also just has 1 leaf. Let's go to this one. This one has 2 leaves. What are they? 12 and 4. All right? So does everybody understand what a leaf is? Okay? Next definition, internal node. An internal node is a node that is not a leaf. Well, that's easy. So does this have any internal nodes? Does this have any internal nodes? Does this have any internal nodes? 5 is the internal node. And the internal nodes here are what? 5 and 3. Okay, so that's the definition of internal node. And complete. A binary tree is complete if every node has either 0 or 2 children.
Just tree 1.
Is this complete?
Yes.
Every node has either, yeah, this is complete. Is this complete?
Yes.
Yeah, is this complete? No. Is this complete?
No.
No. So let's draw another interesting complete tree. suppose you have it, I won't bother to put the values in because it just depends on the shape. Is this complete?
Yeah.
Right, because every node has either 0 or 2. So here are some complete trees.
So big trees will tend to look very symmetrical.
Well, would it? Here, let me ask you this. Is this complete?
Yes.
I think it is, right? Because every node has either 0 or 2 children. This has 2, this has 0, this has 2, this has 2, this has 0, this has 0, and this has 0. Okay? So, I mean, you can't just have just one left child or just one right child. You either have to have none or both.
Can a node have 2 parents?
No. A node cannot have 2 parents. Yeah, this is an interesting species. It's a unisex. Is there such a thing in, maybe in the plant kingdom?
Yeah, maybe plants,
Yeah.
like trees.
Asexual things?
Yeah. But anyway, yeah, so don't confuse, we don't have full here. Yeah, this is an example of a full tree. This is not full, this one is full. Yeah, I don't think we have that definition. Do we have it, that definition? Yeah, well, that's another definition of it. All right, so does everybody understand these definitions? Okay, now, these are all very interesting, but now what we want to see is what are some of their properties and how can we prove them? And obviously what we're going to do is we're going to prove them by using mathematical induction. So this is one of those situations where we're going to have to do some word problems. I mean, this is slightly informal. Okay, so these are like counting exercises. So now check out these theorems. 12.33, the maximum number of nodes in a tree with height n is 2 to the n minus 1. Actually, we can check that one out. Let's see if that one makes sense. What is the height of this tree? What is the height?
3.
1, 2, 3. The height is 3, right?
So
Here height equals 3. 2 to the 3 minus 1 is 2, 4, 8 minus 1 is 7. And we have 1, 2, 3, 4, 5, 6, 7.
And you couldn't have any more in a tree with that height.
Yeah, here, what is the height here?
4.
The height here is 1, 2, 3, 4. The height equals 4. And 2 to the 4 minus 1 is 2, 4, 8, 16 minus 1 is 15. So the maximum number of nodes is 15. The actual number of nodes in this is 1, 2, 3, 4, 5, 6, 7, right? But you could have, I mean, with this height, you could have as many as 15. In fact, if you did, I won't draw it, but if you can visualize it, it'd be 1, 2, 3. It would be 1, 2, 3, and then it would be 4, 5, 6, 7, then it would be 8, 9, 10, 11, 12, 13, 14, 15. You know, you can kind of visualize that. But if you go one more, so that's the maximum. So the maximum number of nodes in a tree of height n is 2 to the n minus 1. Let's take a look at 12.34. The minimum number of nodes in a tree with height n is n.
Sure, you can just keep going without.
So the minimum, you would just have like maybe one left child, one.
But it couldn't be complete.
No, it wouldn't be complete, but that would be the smallest number that you could have with height. So that's an interesting theorem. 12.35, the maximum number of leaves in a tree with height, the maximum number of leaves. So now what are we talking about? Leaves. Yeah. What was the number? Was it pound? Was that number of, no, or was it, no, that was the number of nodes. What was the number of, did we have a number of leaves? We didn't have one for number of leaves. Okay, so here we have, let's do num leaves. Num leaves here is 4, right? 1, 2, 3, 4. So the height here is 3, 2, 4, 8 minus 1 is, 2 to the n minus 1. So 3 minus 1, wait.
Oh, 3 to the 2.
Maximum number of leaves is 2 to the n minus 1.
Which is, it's
And
N
n is 3. 3 minus 1 is 2. 2 squared is 4. And sure enough, there's 4 leaves. And that's the maximum number.
internal nodes.
And then the maximum number of internal nodes is 2 to the n minus 1. Internal nodes.
One less than that.
Yeah, interesting, huh? And then 12.36, the minimum number of leaves with height n, the minimum number of internal nodes. And then 12.37, every non-empty complete tree has an odd number of nodes. Ooh.
Wow.
Hey, here's a complete tree, right? 1, 2, 3, 4, 5, 6. Ah, there's an odd number. All of these,
If it's complete, then every level is even, except for the first one, which just has 1. So it'll always be.
Right.
Oh, yeah.
And it's the same way. 2 to the n minus 1 is always an odd number.
It is. So that's consistent. So these are all true. But what we want to know, obviously, is how to be able to prove them. So let's prove, I think, let's prove 12.33. And the other, there's an,
1235.
I think one of these is,
Let's do
it's probably 1235, yes, because that's what's assigned. So I'll let you prove the others. So let's prove 12.33. Okay. Well, so we want to prove the maximum number of nodes in a tree with height n is 2 to the n minus 1. Now, you're not going to like this because when we get to the induction case, you're going to have to write all that out with n plus 1, assuming and writing all that out with, as the inductive as the inductive hypothesis. So you know who you are, who's not going to like this, but we will proceed anyway. So first of all, we'll do the base case. Okay. So what do we have to prove with the base? We need to prove 12.33
So we need to
for the empty tree. And what is the base case? It's the empty tree. So base case. Okay. So must prove for the empty tree. All right? Well, what is it that we have to prove? Maximum number of nodes in a tree with height n is 2 to the n minus 1. So we have to write that out. So max. So we have to write max nodes, I'll do pound, max number of nodes, a little abbreviation here, max number of nodes in height n tree equals 2 to the n minus 1, right? So this equals, now what is our base case?
base case.
Yeah, base case n equals 0, because doesn't that say for n greater than or equals 0? So base case n equals 0.
And can we do it in the one step so we don't have to do it again?
Yeah, base case n equals 0, and the empty tree has
12, what's that?
12.32.
32. So it tells us that height 0 is the empty set.
12.32, right?
Yeah.
Okay, so base case n equals 0 and 12.32. And 12.32, the empty tree has 0 nodes. So that is 0 equals what? 2 to the what? Oh, this is I didn't write this correctly. This is 2 to the not 2 to the n minus 1 up here. It's 2 to the n up here minus 1 down here. So this is 0 equals 2 to the 0 minus 1 equals, by math is correct, 0 equals 0. Boom, we did the base case.
Induction.
Yeah, now the induction case. It's the one you're not going to like. Because you see, these are we have to use English argument. We have to write this out in English. We have, all right.
Can we do abbreviations again? So like max number of nodes in height n plus 1 tree equals 2 n plus 1 minus 1.
Well, let me show you. Here's how I would write this out. Let DLR, let parentheses DLR be a height n plus 1 tree. Be a height n plus 1 tree. Are you with me here? So this is the one that we're going to have to prove it with, assuming the height n tree, okay? So let DLR be a height n plus 1 tree with, but now, not period, with the maximum number of nodes, because we're trying to prove this maximum number of nodes, right?
Max nodes 2 n plus 1 minus 1.
Well, we'll just say that's what we have to prove. With the maximum,
Oh, we're saying it has that many.
yes, with the maximum number, well, we're saying it has the maximum number.
Right.
With the maximum number of nodes, okay? So that's what DLR is. And what must we prove?
Must prove that DLR.
Prove the maximum number of nodes is 2
That-
1 minus 1.
Now, was the pound the number of nodes?
Yeah.
Okay, so notice 12.31 pound is the number of nodes, right? So what must we prove? Must prove pound DLR equals what?
2 n plus 1 minus 1.
Yeah. So must prove pound DLR equals
2 to the n
2 to the what?
n plus 1.
N plus 1 minus 1 down here, right?
Assuming.
Assuming the what? Max number of nodes in a height n tree, in a height, not n plus 1, not height n plus 1, but height n is,
2 n minus 1.
yeah, as the inductive hypothesis. So we have to write that out. Assuming maximum number of nodes, assuming max number of nodes,
In height entry.
yes, of nodes in height n tree is 2 to the n minus 1 as the inductive hypothesis is correct. All right? So here's the proof of the inductive case. Well, we have to make an observation. We have to see, look, here's a common way. Unfortunately, our book doesn't have very many diagrams in it, but one way to draw a tree in general is to draw it like this, and then down here to have this kind of like represents the left child, which is a tree. And this represents the right child, which is a tree. You see, this is kind of like an abstract. This is kind of like an abstract drawing of a tree. What I'm trying to draw here is like if we come over to here to this tree number 3, it's like this is, you know, this is this, and this is, you see what I mean? It's like each one of these triangles is a subtree. It's the left child, which has a bunch of nodes in it, right? Okay, so here's the point. Here's the point. If you think about the maximum number of tree, if you think about the maximum number of nodes, in order for this n plus 1 tree to have the maximum number of nodes, what has to happen? what must the left subtree have? In order for the whole thing to have the maximum number of nodes,
The left tree has to have the maximum.
the left tree has to have the maximum number of nodes as well as, furthermore, the what? The right tree has to have the maximum number of nodes. Are you with me? So we have to make that observation. So and furthermore, if this whole thing is height n, then each one of these is what? Height n minus 1. Or if this whole thing is height n plus 1, then each one of these is height n. So we make that observation. So here's our proof. L and R must be height n trees, right? So L and R must be height n trees with the maximum number of nodes, right? That's an observation. With the maximum number of nodes. Yeah? So,
That's a good observation.
yeah, in fact, that's the key to the argument. So the number in D, so see this one here, this one is L, this one is R, right? And this is D.
Right.
Are you with me? So what's in this node that's D and this is L and this. So D is the integer and this is L and this is R. So pound D, L, R equals, now you guys, what do we know? Now let's go.
Now we know 2 height n trees, so it's gonna be equal to
But what definition do we quote?
the inductive hypothesis.
No. What's by definition? What is pound DLR?
Oh, sorry. It is 1 plus.
By which theorem? By which definition?
31.
It's 1231. Are you with me?
Yeah.
It's by 1231. So this is, so by definition, 12 by 30. What does that say it is?
1 plus pound L
Yes.
plus pound R.
1 plus pound L plus pound R, right? But this equals by the what?
Inductive hypothesis.
By the inductive hypothesis, right? And what do we know about pound L and pound R by the inductive hypothesis?
Both 2n minus 1.
Yeah, so this is 1 plus 2 to the n minus 1 plus 2 to the n minus 1. So here's our computation, yeah? And so this equals, by some math, now, so 2 times, there's 2 to the n plus 2 to the n, so that's 2 times 2 to the n. And this is 1 minus 1 minus 1, so that's what?
Minus 1.
Minus 1. So this equals, by some more math, so what's 2 times 2 to the n?
2 to the n plus 1.
So this is 2 to the n plus 1, minus 1. And isn't that what we were trying to prove? Over here. Isn't that what we were trying to prove?
Yep.
Boom. Are we good? So I think what your job, I think I assigned 12.35. Is that what you anticipated? All right.
Not bad.
So yeah, so what you'll need to do is, it takes writing out stuff, you know, I mean, it's not, and you have to make this observation. Notice the key thing here is this observation. Now with 12.35, it's the maximum number of leaves. Well, in order for this to have the maximum number of leaves, in order for the tree like this to have the maximum number of leaves, what has to happen? This has to have the maximum number of leaves, and this has to have the maximum number of leaves. So it's the same kind of argument. Yeah? Are we good?
And, internal nodes can have 1 or 2
Children.
right?
Yeah.
Okay.
Yeah.
But we're looking at the maximum, so it's definitely going to have 2 children.
Yes. Yes, that's a good point.
Well, I guess the last one doesn't necessarily have to.
The last one, what do you mean the last?
The last like tier. That's the right word. Like they can just have one child each. It doesn't really matter because that's the last like.
Well, a leaf.
It does, because it doesn't have to have the maximum number of leaves.
Just the maximum number of internal nodes, and so the last.
For 1235B, it doesn't matter how many.
The maximum number of internal. Oh, right.
It can have the minimum number of leaves and the maximum number of nodes.
Right. The maximum number of internal nodes. Well, this would have to have the maximum number of internal nodes, and this would have to have the maximum number of internal nodes. So it would be however many internal plus maximum. Yeah, yeah. Oh, I see what you're saying. For this to have the maximum number of internal nodes, it's not necessary that L and R have the maximum number of leaves.
Right.
Right.
Yeah, you're right about that.
Pretty close to it.
Yeah, you guys are good. All right. Now, we are moving on to the next topic. Now, let me give you a word of point of information here for our next topic. I have entitled, if you take a look at your equation sheet, I have changed the numbering system slightly. Now, it's the next page, the next section in your handout it's titled A Theory of Programs, and these axioms and theorems are numbered starting with the letter P. P for programs. Now here's why we're doing it this way. In the first place, what our author has done is he has scattered this material about the application of formal methods to programs in several different chapters. In fact, I don't know if you remember, I hope you remember, at the very beginning of the semester last year, last semester, we talked about we're going to redo the Hoare triple. And we did the assignment statement, and then he has some information about loops in one chapter, and he has some information about some other material in another chapter. So rather than have, and I have been skipping some material up until now. We've been skipping some of this material. Because I think it's better, the way I prefer to present this is to consolidate it all into one topic and learn it all at one time. So that's the first reason. The second reason is that there is a lot of material here. There is some material here that's not in the book at all. Okay? And in fact, if you look here, P1 through P9, none of this material is in the book the way it is done here. And
Guarded command language?
it is guarded command language. And let me show you, if you go to, let me see, P10, that's not in here. But now here, over here, like if you look at P19, proof method for assignment, P19 is, I have a little note up here in your handout, P19 is 10.2. And over here, the IFG, that's what we call P21. I just have a little note over here, P.21 is 10.6. So you can refer back to these if you want to read about this material in the book. You can refer back to it. But the point is that this material, a lot of this material is not in the book, so you'll just have to get it from the lecture and from this handout, okay? And that's why the numbering is a little bit different. Now, this is a little bit crazy. I should have. Look at here on the equation sheet. We have a P.4 and a P.4.1 and then a P.5. Well, none of these are in the book, but after I had typeset this whole thing, I thought, oh shoot, I need to have another theorem in here. That would be really nice to put in there. And I just didn't want to go through and renumber all my equation sheets. So anyway, that's explanation for that little thing. All right.
The P.6 something dot something is usually the ones that you.
Is usually, are usually the ones that I put in that are not in the book, but none of those P's are in the book, you know, hardly any of those P's are in the book. Because we're going to do it, I want to go into it in a little bit more systematically and also in a little bit more depth and use the concept of the weakest precondition that he doesn't explain in the book. All right, now, so first thing we have to learn is specification, all right? The idea behind a specification. And here's, I want to write down what this is just colloquially, just informally, okay? To specify a program, is to say what it should do. Not how it should do it. And this, I tell you, is a very important concept in software engineering. The key words here are what and how. We have to understand the difference between, yeah, well, to say what, not how, yeah. Not how, yeah. Not how is, yeah. Okay? So, and this is really key. Separating out the specification from the implementation. What, you know, if the specification is what, the word we use for saying what is specification. The word for saying how is implementation, right? Now, have you guys done in your C++? Do you guys know the difference between the .h file and the .cpp file? I mean, you know H. I mean, you know what header files are.
Yeah.
.h files.
Specify everything you can do.
Yeah. In fact, in that programming language in C++, that is the distinction between the .h file and the .cpp file, or the .c.
The header is what?
The header is the specification that says what.
It doesn't actually have any.
Implementation. It does not have any implementation in it. You know? Because what that says is, that says what your methods are, what your functions are, what the parameter lists are, all right? And any documentation that you have normally goes in that header file, goes in that file, and that explains what the functions do. But then in the implementation file, then it does it. And if you are just going to be, if you are writing a library of routines for someone else to use, the person who's using those doesn't need to know how. All he needs to know is what. And, oh, it does this. I don't care how it does it. It does it. So that's what a specification is. Now, this all is related now to the Hoare triple. Okay? So recall from section 1.6 that a state, what's a state? Definition of state? A list of the what and their what?
Variables and the values.
Their variables and their values. Okay? So that's the identifier value pairs, variable value pairs. Further, the Hoare triple, QSR, where S is a program statement, Q is the precondition, and R is the postcondition, has the interpretation. Now, can you please tell me, I hope you still know, what is the interpretation of this Hoare triple QSR?
Q is the precondition.
Yeah, Q is a precondition, S is a statement, and Q is a...
S
R.
executes.
Oh, yeah, okay, so what is the interpretation? If what?
If Q is true,
If Q is true,
null state, right?
well,
Or just
no. If Q is true,
In whatever state.
yeah, in the beginning,
and S executes,
yeah, good, and S executes, what will it do?
terminates,
It will terminate, and what?
and R
Is what? What's the word?
Guaranteed to be true.
And R is guaranteed to be true. Okay, so here, that's exactly right. So execution of S begun in any state in which Q is true is guaranteed to terminate and R is true in the final state. That's the interpretation of the Hoare triple. All right? Now, this Hoare triple is the key to writing down a specification. Are you with me? This Hoare triple is the key to writing down a formal specification. So here is a formal specification. A formal specification, a specification of a program should give. Now, how many parts to the Hoare triple are there? Obviously, there's 3 parts. So now, here's my question. Those 3 parts of the Hoare triple, 2 of those are given and 1 is left out.
Statements left out.
Exactly. Because the statement is the implementation. So, a specification gives a precondition, Q. Okay, so that's a Boolean expression that describes the initial states for which the execution of the program is defined, right? And then what happens is the middle one is the one that's left out. So, instead of actually writing down the statements, what we do is we write down a list of variables that we expect the program to change. Are you with me? And they are changed in such a way that what happens? The post condition is guaranteed to be true. See? So, here is what it looks like. Here is what a formal specification looks like. It looks like this. Now,
That's how we program, right? That's how we decide how to implement, how to get from Q to R.
well, when we program, what we're doing is we're filling in the question mark.
Right.
I mean, what we're doing
Asking
is
ourselves that question.
we're asking ourselves this question. Yeah, this is a question mark. Yeah. Okay? But anyway, but the important thing is, what a specification is we're given the Q and we're given the R, and here we only just specify, well, X is going to change in such a way that, we don't know how it's going to change, but it's going to change in such a way that this is true. So we leave out the middle one. So that's why we have the question mark in the middle. Now, I want to emphasize that this, and I don't know how many times, I'm going to make a prediction. I'm going to make a prediction that the next time on the next exam, and I wish that this were not true, so I hope you can prove me wrong. My prediction is there's going to be a question on the next exam that's going to be to say, write the specification for blah, 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 blah. Anytime you have a task to write a specification, what must your specification look like? It must start with a what? With a left brace, and then a Boolean expression, and a right brace, and then X, and then something with a question mark in the middle, and then a curly brace, and a post condition, and a curly brace. There will be some people in here who, when I say write the specification, will not start with left curly brace. And that will be incorrect. I don't know what I need to do whenever I say write a specification, and they say, what do you mean? Well, what we mean is write a left brace and a precondition and a right brace, and then an X gets and a question mark here, and then a brace, and then a postcondition and a brace. This is what a specification, formal specification, looks like. This is the shape of a formal specification. And I always try to emphasize this, and I'll ask you this over and over again in hopes that you'll get it. And I hope that you can prove me wrong. On the next exam, whenever I say write a form, or on the next homework when I say write a formal specification, and you say, what do you mean? What do we mean is write a left curly brace, write a precondition, write the right curly brace.
Are we going to look at some examples?
Oh, obviously, we're going to look at a bunch of them. And in fact, your homework assignment, not for tomorrow, but for Monday, will be to write some formal specifications. And we'll do a whole bunch of examples tomorrow, or on Thursday, okay? But the main thing I want you to get is that this is what a formal specification looks like, okay? And we'll start with, and then we'll continue on here on Thursday. Great. All right, see you next time.